Hi everyone, this is my project on transformable and deployable structures. To introduce myself, I'm Caroline Yanson, a third-year architecture major. For my project, I explored transformable and deployable structures, which are structures that have many components and are connected through scissor hinges. So these structures evolved in history. They started off with simple applications like Egyptian hunting chairs and Mongolian nomadic yurts, but today we use them almost every day without even realizing it. For example, we use them in umbrellas. Store uses them to lock their doors. They're used in tents, foldable furniture, telescopes, tripods, elevator doors, and so much more. The first case study I looked at was the universal scissor component. This development was worked on by students in London. This is the development of a universal component. Usually, scissor components in transformable and deployable structures are complex and generally designed for a single purpose. But by creating a universal scissor component, it allows the design to be simpler and it can be used to different applications of the structure because it can be mass produced and applied to different shapes and sizes. The adaptability of a uniformed component will ultimately lower the production cost and make it easier and faster to set up and take down. The second case study I looked at was the Hoberman Arch, created by Chuck Hoberman for the 2002 Olympics. This structure is basically a motor-operated aluminum arch that expands and contracts, similar to the iris of a human eye. This last case study I looked at was a transformable dome. I found this interesting because they used a rigid covering, which allowed it to be protected from the weather. But what was interesting about this one was the fact that they installed them as modules so that if one needed repair, they would not have to take apart the whole system. So my thesis was ultimately that if I learned the possibilities of transformable and deployable structures by exploring different online simulations, modeling a transformable and deployable structure out of a toy kit, and finally by 3D printing a scissor hinge, then I will be able to develop a comprehensive understanding of how transformable structures work, also within the context of the architecture, engineering, and construction industry. My newly gained knowledge of kinetic and adaptable and flexible structures could then help me in my future career in designing sustainable, dynamic structures that can be used for different needs and purposes. So to do this, I completed my project in 3 parts. For the first part of my project, I tested out different online simulations of scissor hinges and scissor forms. So here, these are 2 examples of the types I used, but altogether I used the scissor hinge simulation, the expanding fence simulation, an expanding tower simulation, and a deployable shelter simulation. And I experimented with these by changing the control variables that go into making the components of all of these structures. So through my demonstrated simulations, I learned that by using a scissor hinge type, I can create numerous forms of transformable structures and the visualization helped me get some clarity on how the hinge actually works, and that the least amount of components to a scissor hinge gives more of a lightweight and compressed structure that will be easier to store and transport. Part 2 of my project was assembling a Canucks toy Hoberman sphere. To do this, I followed a tutorial I found online. And so basically, through this sphere, I gained knowledge in how the scissor hinges actually join together, and how they are joined together through both 2D hinges and 3D hinges. I learned that there were also much more pieces involved in creating the deployable sphere than I thought. Because this process involved a lot of parts, I think that if this were to be mass fabricated, it would be much more efficient to put together as well as manufacture. Go. Thanks. Lastly, part 3 of my video was to 3D print scissor hinges. And so to do this, I had to get an online 3D model that I got from an open source 3D printing website. So I got a 3D model of a Hoberman sphere, and then from this, I took 2 parts of the Hoberman sphere that I wanted to print. So I decided to print the 3D hinge right up here, and then the 2D hinge on the bottom. So these 4 pieces are the pieces I needed to create the hinges. So from here, I extracted the individual pieces and uploaded them separately to a 3D printing software called Cura, where I did separate prints of each of these pieces. From here, I uploaded the Cura files to the 3D printer through a USB, changed the printer's filament, and pressed start. And in total, to 3D print them only took about 3 hours in total. Here are the final results of my 3D printed parts on the top. I did not end up needing the caps, which are the second picture on the top row. And the bottom row is the pictures of the final assembly for the 2D hinge and then the 3D hinge. I will say for the assembly of them, I had to take an X-Acto knife and trim the original parts to make them fit together better, because the 3D printing left extra thickness that I wasn't anticipating. Ultimately, I achieved my goal by successfully learning about different forms of transformable and deployable structures through the demonstrated simulations, by physically modeling my own Hoberman sphere, and by 3D printing my own scissor hinges. I can design my own transformable and deployable structures in the future. Because I want to specialize in humanitarian architecture and social infrastructure, I could use my newly gained knowledge to create flexible, portable, and easy to erect structures that are sustainable, leaving no permanent damage to the site or mark on the site at all. Some practical implications of what I could design from my new knowledge could be COVID-19 vaccination hubs, social distancing igloos, shelters in natural disasters, or more. I think more temporary spaces like these are needed in our built environment, because in times of crisis, these structures can quickly serve an essential purpose. So I feel a lot more prepared going into the architecture field, because I learned the importance of overall testing conditions, making physical models, and learning and keeping up with AEC computer programs. And overall, I learned that the characteristics of flexibility, adaptability, reuse, transformability also lead to a sustainable, more developed project.